Hello and welcome everyone to Red Planet Live. I am your host, Ashton Zeth. I am elated to be hosting the Mars Society's podcast and leading the conversation about human exploration of the universe and the future settlement of Mars. As a longtime space enthusiast, I am passionate about STEM education and making humanity an interplanetary species. Thank you everybody for joining today and supporting Red Planet Live. Now, going to kick off today's episode the same way we always do. Couple Mars Society announcements, exciting things happening over here at the Mars Society. The first is that the Mars Society has officially launched a capital campaign to upgrade the Mars Desert Research Station, also known as MDRS, which is a vital habitat where scientists, engineers, students simulate life on Mars here on Earth. So your donation directly supports critical improvements to this one-of-a-kind research facility in the Utah desert, and every donation does come with a special perk as a thank you for being part of the mission. Head to marssociety.org to learn more and to contribute. Also, we have the 2025 International Mars Society Convention coming up, scheduled for October 9th to the 11th at the University of Southern California in Los Angeles. That is USC in LA. We are celebrating the 28th year, and this global conference will focus on Mars exploration, human settlement planning, and cutting-edge technologies. Now, this year's theme is Mars, the Time Has Come, which is so fitting because it aligns with the U.S. government's recent announcement to prioritize a near-term human mission to Mars. Also, if you want to contribute to groundbreaking research or have innovative ideas to share, now is your chance. You can officially submit your abstract for the Mars Society Convention. You can submit your proposal at the website that you see right there. Go to the Mars Society's website. Submit your proposal by June 30th to be considered for a speaker at the convention. Don't miss this opportunity to help shape the future of Mars exploration. All right. Announcements out of the way. Excited to introduce today's guest. Dr. Luther Beegle is a distinguished scientist specializing in planetary science and astrobiology. He earned his PhD in astrophysics from the University of Alabama at Birmingham in 1987 and a bachelor's in physics and astronomy from the University of Delaware. Dr. Beegle has dedicated over 2 decades to the Jet Propulsion Laboratory, JPL, where he has held significant roles, including principal investigator for the SHERLOC instrument on the NASA Mars Perseverance rover, and as a principal researcher in the science division. His research has primarily focused on developing technology to detect and characterize organic molecules in an effort to identify potential biosignatures on Mars. In 2023, Dr. Beegle joined Northrop Grumman at Space Park in Manhattan Beach as a member of the basic research for DoD-related science missions. He is currently working with NASA's Langley Research Center on development of the next generation of technology for planetary missions. Luther, thank you so much for being here.
Thank you very much for having me. I appreciate it.
I'm excited to chat with you. And, I had an opportunity to watch your presentation from the Mars Society Convention a couple of years ago. So we're definitely going to touch on that. But perfect timing. We have our next convention coming up. So maybe there's an opportunity that since we're going to be close by, we're going to have you at the next one. So
yeah, those conventions for the Mars Society are always really fascinating. There are a lot of really good, enthusiastic group of people coming, and it's a can-do thing. I like that.
It's always a great opportunity to meet different people from the industry, learn something, make some good connections, and walk away excited about the future of Mars.
Yeah.
All right, well, we're going to kick off the conversation today the way we always do with question of the day. There's no right or wrong answer, I promise. It's just meant to be an icebreaker, just to get your opinion. So today's question of the day is, if a movie reel was made about your life, what core memory would you have to have highlighted?
This is a relatively easy one, which would be the birth of my son on 9/11. So it would involve both the birth and the towers and everything, and it would have been an interesting little reel that would have gone in because it was the weirdest day ever. So for multiple reasons.
Right. I can't imagine the highs and the lows on a single day. I thought you were going to say, Perseverance landing.
That's the yeah. That would have been a good one. Perseverance, law, and selection, finishing my PhD. But 9/11 really sticks out. If you know anything about LA traffic, we drove from Pasadena to Sunset in 50 minutes at 5 o'clock at night because there was nobody on the road, and it was just a really weird day.
Yeah, I can imagine. And now every day or every 9/11 since then, I mean, obviously you're celebrating, your
Yeah.
son's birthday, but at the same time, those memories of that day always, come back.
Exactly.
When well, I would have to say for myself, I still got lots of memories to make, but I would say for myself, I'd have to highlight my wedding. It was such a beautiful day, surrounded by my favorite people. So I think I have to show that in my highlight reel.
Yeah, that would be great.
All right, well, let's jump into it. I want to remind everybody that's listening, if you have questions, please submit those in the chat. I will try to sprinkle those in throughout the conversation. But gonna start, at the beginning, like we usually do. Luther, tell us, did you always envision yourself being a scientist? Did you imagine yourself working on technology built for Mars when you were?
Yeah, not necessarily technology for Mars specifically, but I always was fascinated by space. I always was drawn to astronomy and science fiction, and would read nothing but science fiction growing up. Loved thinking about all the different possibilities out there. And then I got a chance to go to graduate school and work for somebody who had worked for NASA, Professor Tom Dowyak. And he taught me a lot and taught me, we started writing proposals for instruments, and we started really thinking about how could you do some of the things everybody wanted to do? Like, what does it mean to go look for life? What does it mean to see an organic molecule? What do all those things really mean in context?
Mm-hmm.
And it's something that I was always drawn to, and still dabble into this day. It's completely open-ended, and it's what you can make of it, and your imagination can take you away, and it's great.
Mm-hmm. You mentioned you liked reading sci-fi. I'm always kind of itching for something nostalgic. Do you have a good recommendation for me? A good sci-fi book I should read?
My favorite set of books were the Foundation series by Asimov. I read those. I pick them up every 5 or 10 years and read them, or the robot books, Caves of Steel. That trilogy was also great because it really helped. It really made you think about what the future was like and what could possibly be in. And there's not a lot that actually goes on in the first Foundation book, which is why the series is so interesting, because they've filmed a book that I thought was unfilmable and made it into a pretty decent series.
Okay, this is a good one. I'm not as familiar with this, so it's going on my list. My list seems to grow faster than I can check them off, but I'm adding them onto my list. So thank you. Let's see. Well, with your career, tell us about your time at JPL, your time with NASA, specifically as principal investigator for the SHERLOC instrument on the Perseverance rover.
Yeah, so I went to graduate school, and at graduate school we started working on. We wrote a proposal for what's called a Raman spectrometer to miniaturize it. These spectrometers back in the 90s were the size of rooms, and we wrote a proposal. We thought we had an idea of how to make it smaller, and that was like 1994, 95, and we got that funded, got some money out, and in the meantime, I had gotten a postdoc position at JPL. So I came out, being from the East Coast, I'm from Philly. I'm from outside of Philly, Delaware. Living in LA was not something that I'd ever imagined I would do. So I came out for a year or two. Now I own land, and I've been here for almost 30 years. So it wasn't really sure what I was going to do. And once we got here, there was a paper that came out in 1996, which really fundamentally changed looking for life on Mars and astrobiology. And that paper was a paper by Dave McKay et al. And what it said was, it was in Science, and they thought they saw evidence of life in a Martian meteorite, which really took everybody by surprise. And it was like a really good paper. And what that paper showed more than anything else is that how you do a measurement really is important to how to determine what's in that paper, or what's in the rock. As other people looked at that rock, they came to the conclusion that maybe there was no life associated with it after all. But it really did show us that we had no idea how to do any of this. So I don't know if you've ever seen the movie Contact.
Mm-hmm. Oh, yeah.
The Bill Clinton discussion in that movie is based on the Martian rock, Allen Hills 84001. So he actually came up and had a press conference about that after they announced life was in the rock and everything. And so we really started thinking about, how do you do all of this? What does it mean to look for life? What does it mean to not to see something or not see something? How do you make something smaller? How do you make it more flexible, more able to do different things? And that's kind of the path we went down. So we tried a lot of things that didn't work, which is always a wonderful thing in technology building, is things that don't work. And so you take that and you learn from it, and you do something different, and you do something different. And then eventually we came back around to do Raman again, which is in the early 2010s. And we wrote a great proposal, and that proposal got selected, and then we built the instrument and flew it.
Tell us about the instruments aboard Perseverance. I just happened to recently be writing an article for an assignment, actually, for my master's program, and talking about Perseverance. And that's part of why I thought, oh, maybe that would be in your highlight reel. But tell us about working on that mission, what specifically your role was, how you contributed to the instruments that was on Perseverance, and then the data that came back from Perseverance. Obviously, we're still getting some of that information, but what did it look like post-landing?
So it's interesting, because what you're doing is you've got a mission, and everything, there were 7 different instruments on that mission, and they were all trying to come together, and we were all trying to put them on the rover. We're all in development at the same time. We're trying to do our little miracle of an instrument. Other people are doing their little miracles of an instrument, and trying to get everything together with being able to accommodate it on the rover, because we kind of knew what the rover was going to look like. So if you ask me why does SHERLOC do some of the things it does, the answer normally is because that's what the rover could do. So we took advantage of that when we built it. So in the development stage, you had all of the other PIs, all of the other teams were trying to get the most out of their instruments, Moxie, Pixel, SuperCam, Mastcam Z, RimFax, and SHERLOC. That's 7. Putting everything together, and then thinking about what's going to happen. And what you don't realize is that with all these instruments, all this development, is that everybody has what they want to do, and then there's what you want to do. And what you want to do is usually the most important things to you. So you basically have a discussion with a bunch of other people, and you try to negotiate your way out of things. So that's one thing that was really surprising, is how much negotiation went on. So, can we use our instrument today? The answer is no, we have to use Moxie. Can we use our instrument today? No, we're going to use RimFax today. Can we use our instrument today? And that would happen a lot, and there was a lot of frustration about that. But other than that, we landed. We got great pictures. We got some great science results at the beginning, and that's and it was just wonderful to be part of.
So we've obviously seen the Mars sample return mission be delayed. A couple of reasons for that. What do you think is the future for Mars sample return?
So if you want to send humans to Mars, I think that everybody agrees that you have to do sample return before you send humans to Mars. And that's one reason you have to do sample return. The second reason is it's really hard to imagine how you identify life robotically. We argue all the time about rocks on the Earth that we found in Australia and Greenland on whether they had life in them. And I'm pretty sure that life started on the Earth at some point. So we already know the answer to it here. The question is, can you do a robotic mission to detect life on Mars unambiguously? And I don't know. I don't think that's possible. I think you have to bring the samples back to get looked at from laboratory instruments with people in the loop, with the ability to change your instrument. So one of the things that is really interesting, and this has come up in multiple different missions, is that we defined all of SHERLOC's capabilities in 2013 and 2014. If anything had been found after that we could have taken advantage of, we wouldn't have been able to take advantage of it because we were too far down the developmental path. The sample analysis on Mars, instrument SAM, on Curiosity, their technology cutoff was before Phoenix. So anything that Phoenix found, they couldn't respond to. But if you bring them back, you have the ability to do that. So if you're going to go look for life on Mars, you have to bring the samples back. You've got to look at them in a terrestrial lab, and you've got to have multiple different people with multiple different instruments looking at it. From a humans to Mars perspective, you have to bring those samples back because you don't know how toxic that dust is. There's a lot of other properties of the dust you're not going to be able to measure in situ, including size and shape down to the 1 micron size particles. And all of that really does interact with how people are going to be able to move around on the surface, breathe on the surface. They're not going to breathe outside, but they'll breathe inside. But hypothetically, they go outside, they come back inside. And what we found from Apollo is that dust from the moon came inside with them, and they breathed in the dust from the moon. You want to make sure that if they're stuck on Mars for a year, that they're able to breathe the dust without it becoming potentially life-ending. So you have to do sample return, and everybody agrees on this. And the question though is that how much are you willing to pay for that sample to come back? And so in the last decadal survey, the people that wrote the decadal survey and general got community approval was we want to pay $5 billion for sample return. And as they started to do sample return, start thinking about actually what it was going to cost, that number rose pretty dramatically to like well over 10 billion. And so then the question everybody should be asking themselves, are the samples that Perseverance found really all that great and all that we have to bring this back to justify the $11 billion number? Because if you bring them back, you might answer the humans to Mars question, but the question about whether there's life in those samples, if you don't have a good sample, if you don't have a sample from a place that life could have started, you're going to have to go back and look again. And so now instead of $11 billion, you're going to spend another 11 billion and another 11 billion plus bringing it back. So I don't know the answer to whether or not it's 11 billion. I don't have that much money. I would write the check if I did. But I think that somebody in the scientific community should look at the results from Perseverance and analyze what we found from Perseverance and look at what we know from Mars meteorites and from other Mars missions and make the case that these are so unique of samples that we have to bring them back. And if somebody did that, then that would help me either get on board or not get on board with bringing those particular samples back.
Those particular samples. I've heard, I think it was recently Rocket Lab, I think it was Peter Beck with Rocket Lab had said, hey, there may be interest in Rocket Lab trying to collect those samples and bring it back. A couple episodes ago, I spoke with Jim Cantrell, and he was talking about the launch windows. And so we could see robotic missions going in 4, 6, potentially 8 years. Yeah. So maybe SpaceX would be an option to bring those back. Yeah. From your perspective, traditionally, the rover, specifically Perseverance, was a NASA mission, obviously with partnership with other organizations. Do you think that it would still be effective? It would still be a good partnership to have one of those commercial companies like Rocket Lab or SpaceX bring those back? Or is there a reason that we may want to keep it in-house within NASA?
I would believe anybody who could do it for the price point that NASA could afford would be good to do it. The problem with that, though, is that what we found from the CLIPS missions, and the CLIPS missions are awesome. I've been kind of involved in a few of those, but the CLIPS missions to the moon we've learned that it's really hard to do a lot of these things. So if we go to a third party that's never landed on Mars, that's never brought anything back from Mars, that doesn't have all of that institutional knowledge. The question is it going to work? And you'd have to make that decision based on good engineering practices and everything else like that. And so if Rocket Lab could bring them back for $4 billion, I'm 100% in, but they'd have to show that they can do that without a learning curve. Because, we made landing on Mars seem really easy the last 4 or 5 times, but there were a bunch of ones that didn't work. There's a bunch of Russian Mars missions that never made it, never worked. We've had a couple failures. And so they would have to know that it's not just we're going to go try this and see if it works. Because if they bring in those samples back and it explodes, you've lost those samples and you've got to go back to the starting point. So but anything the commercial community can do is 100% behind, because they do have the ability to do things that NASA can't.
We've previously talked about on the podcast before the possibility that anything that you send to Mars could potentially contaminate those samples. And then, it's critical that the analyzing of those samples, we're able to remove any potential such contaminants. How do we ensure that there is no contamination? So assuming, hey, we've got a vehicle that's going to collect those samples, how do we ensure that there is no contamination and that those samples are valid?
You do the best you can setting it up. You have good planetary protection plan. You clean the spacecraft, and then you re-clean the spacecraft, and then you re-clean the spacecraft. You continue to clean things all the time. When you which brings us to the next point, is what happens when you bring them back. You can't just bring them back in a lab and put them on somebody's desk like they do in Antarctica. And my friends with Antarctic rocks all over the place. And you're like, well, aren't they getting contaminated? And they're like, don't worry about it. But if you're going to need a containment facility, I don't know how much the containment facility costs. I know how many commas are in the cost. It's at least 2 commas. I don't know, maybe 3 commas. So you're going to have to pay for that as well. And you're going to have to find out a plan to make sure those samples don't get contaminated. And it's much more difficult than the biosafety labs we have now, which like study anthrax and things like that, because they don't care how dirty it gets. They can bring all the bugs in. They just don't want the anthrax and the Ebola stuff to get out. Yeah. This facility that you're going to build for the Mars samples, you have to keep everything out and keep everything in at the same time. And I don't know how to do that. I don't know if anybody really, really knows how to do that. So it's a series of questions, and every time you start asking these questions, you can just hear 10 million, 10 million, 100 million, 100 million.
Cha-ching,
yeah, cha-ching, cha-ching.
Exactly. Well, hey, there's been some recent news about Mars and some potential samples and biosignatures. I think it was the Curiosity rover was located, some long organic molecules, had some fatty acids maybe. So for those that aren't familiar, tell us a little bit about what that sample was, what it means, what is it?
So it was one of the samples that we did really early in the mission, and I worked on Curiosity as well. We landed at a place that we called Yellowknife Bay, and we went over and we drilled 2 spots relatively quickly into the mission. It was like 100, 200 days into the mission, and they were called Cumberland and John Klein. And so we got over there, we looked at Cumberland, and they had a piece of Cumberland still in the SAM system. At the time, SAM was still working out its bugs because it's a brand spanking new instrument. They did not have an instrument in the lab that is 100% exactly like SAM. And so I just saw this paper a couple of days ago, and what they did then is they've spent the last 12 years reanalyzing the data they got from that first sample at Cumberland. And they did find material in there that is really looks like it could be these building blocks of a fatty acid. And if that's the case, and if it's true, it's really cool, because it'd be the first time we've ever seen a long chain hydrocarbon on the surface. And that's groundbreaking, because One of the reasons is the surface is really inhospitable to organics. So there's a lot of oxidization that goes on there. And if these things can survive in there, that does really help support the idea that we can go look for life and actually find something that hasn't been destroyed over the 4 billion years since it's sitting on the surface. It's a really great result. It's a really good, cool paper. They did a really, really good job on it.
Excellent. Okay, so we've got some optimism there. Let's see. Speaking of the samples, there's a question here from Thomas who asks if there's any concern China might grab the samples first.
There is. China has been very enthusiastic about things. I'm sure they could probably go pick it up and try to bring it back. I do not know what would happen. That's outside my pay grade and my major. Geopolitically, I'm not sure what would happen then. But we would know it's happening well in advance of it actually happening. And I don't know if they have the $11 billion to go do that sample mission too, because it's going to cost the same amount for them as it will for us if they're going to try to do it, because everybody would know they were doing it. And that's fascinating. It's a really interesting question. I think it would make a good book. Somebody should write that. I'd read it.
Hey, maybe you should write it. With your experience, I mean, maybe you're the right person to.
That would be well. It's a great idea.
Let's see. I've got another question here. What advice do you have for aspiring researchers who want to commit to this field, given all the uncertainty regarding funding, career development?
That's a great question. I work with a couple of nonprofits in the area, and I talk to high school students all the time, and I'm doing it tomorrow for first generation college students. And it's the same, no matter what your goal is. And I have a daughter in college and a son who's getting ready to graduate. It's find something you like to do. And there's always going to be questions about funding. There's going to be questions about the future. There's going to be questions on whether this is stable or not. But if you really find something you love to do and you do it, you'll be really good at it, and you'll continue to go down that path. And one of the best things about this particular field is that it allows you to use your imagination. And I know a lot of people who started down this path and decided to go in different directions, and they had the experience and imagination to be able to draw out different paths, and they're very good. If you find something, if you really enjoy doing something that you can do, that's really the highlight of figuring things out.
What's the saying? If you love what you do, you never work a day in your life. Is that it?
Right. Yeah, pretty much. And also, it's basic problem solving. That the entire field of planetary science, astrophysics, and earth science is problem solving, and that always is in fashion. People need more problem solvers, and people who are able to discuss what they do, which is what you really learn in this field, and those other fields as well.
We talk a lot about Mars because obviously we're the Mars Society, and that's where our focuses are. But I've had an opportunity to speak with other astrobiologists, and we've talked about some of the other missions that are happening, and focus on, like, for example, Titan or Enceladus, and search for life there. Can you give us just a snippet of kind of the planetary sciences for those other potential places?
So yeah, there's some really cool places in the solar system. I can't wait for Europa Clipper to make it to Jupiter and actually tell us more about Europa. In order to, there's been a series of ideas on how to investigate Europa. Europa has more water than the Earth does. Getting Europa Clipper into orbit, understanding what Europa is about, how thick that ice layer is, how whether or not you actually can get to the ocean with any technology we have, all of that would be really cool. I mean, driving a submarine around Europa would be awesome. That's a place that I even in 2001: A Space Odyssey, they talk about the potential of life on Europa, which is really, really cool. That mission's really hard to do. That mission will take a lot of money too. And this is the problem with going back to the sample return. This is the problem of sample return. You've got a limited set of funds. You have a whole bunch of really cool places to go. And so really what makes the most sense, because you can't do everything. And so once Europa Orbiter gets there, once Europa shows what that is, I would really advocate for a lander to be starting to be developed for Europa, because that's a great place. The other two, Enceladus and Titan, there's a mission to Titan, Dragonfly. I don't know if you've talked about that, but that's a really cool, it's a quadcopter. It's got a couple of mass spectrometers. Titan has more hydrocarbons on it than anywhere else in the solar system. It's planet drill baby, I guess is what somebody called it once. And understanding what that chemistry is like on Titan really would help us understand what the chemistry was on the early Earth. And that's going to be a fascinating mission when it launches in either 27 or 28. And that's another 8-year cruise. So, we should be there in 2025 or so. And that's a great mission. And Enceladus is also a fascinating one, where in theory, that there's a liquid ocean on Enceladus. I think most of the scientific community believes that, and it's flying things off into space. There's geysers, and in theory, you can fly through it and identify that. That would be another mission that I would really love to see done correctly, and it would be awesome, because if there's life in the solar system, those are the three most important bodies to go visit, to really understand things other than Mars. And for both Europa and Enceladus, there's a really good chance there's extant life on that surface. And by really good chance, I'm not talking like 90%. I'm talking non-zero. And on Mars, it looks like it's a pretty dry, dead planet. And so if there was life, it's most likely extinct, unless it's way down in the surface, because drilling on Mars is something I would really like to do as well. Get down 20, 30, 50 kilometers to the ice that I just discovered the other day, that I found out about an hour ago. Drilling down into that ice layer would be really awesome as well. And that's technology that is being developed, and would really be cool to be able to get subsurface Mars and bring it back and see if there's anything life in there. I'm worried. I'm always worried that with extinct life, it's going to be hard to convince people. But if you found extant life would be pretty easy. Look, we found a fish on Europa. You can't argue about it.
You read my mind. That was going to be the next thing that I asked you is, what if there is some sample that, the scientific community says, yes, this is a sign, but of course there are going to be conflicting viewpoints. There's going to be, an argument about, is this in fact life? And then how do we validate and confirm that, yes, this is life? And if the scientific community collectively said, yes, this is a sign of life, would that mean, hey, we're going to get all this funding now? We found life. Let's send our resources there. But how do we confirm, yes, how do we all agree that, yes, it's life?
So I don't think you'll ever convince everybody. I just throwing that out the window right now. But what you can do is, we talk a lot about confidence levels, and what confidence levels you are. The two stories that I've talked to people who were involved in their discovery. One was the KT boundary, the comet that wiped out the dinosaurs, and we're still arguing about that all these years later. We're on the Earth. We have all this evidence. And we still have people arguing on whether or not it was a comet, was other things like that. It's really hard to do. And then the plate tectonics took 30, 40 years before the main field geologists bought plate tectonics. Life on Mars is like that. There are still people that believe Allen Hills 84001 had biosignatures in it. I don't know what the percentage is. It's probably like 5-10% of the community. But it hasn't changed much in the past 30 years. And if we found something like that on Mars today, you're hoping to get like 60-70% of the scientific community to have buy-in. Scientists like to argue and like to poke at things, and that's what we do. That's what our enjoyment is.
That's part of the job.
It's part of the job, and you always are going back in and looking at your research and making sure it's correct, and then going back again and believing that the ancient fossils and Earth samples, there's still some people that don't believe those microfossils and stromatolites from 3.8, 3.9 billion years are real. They'll argue that it's something else. And I know life started on the Earth. I know it happened on the Earth. So on Mars, you never know. So it's going to be that argument will go on long after I'm no longer here, or my head is in a jar in terms of whatever that show was, Futurama.
Yeah, Futurama. I love that. What do you say? Like, what is your quick and short answer to anybody that says like dinosaurs not real? Like you got the group that are flat earthers. There was no dinosaurs. There was no comet asteroid that hit Earth. Like, I get that question sometimes because people know that like I host the podcast and I get to interview people, and so they ask me those questions. And granted, I am not a scientist, so I don't have like, here's my body of work and my 20 years of research to prove it to you. What is your quick and short answer to people that say that? What can I tell people?
So my son goes to school over in Prescott, Arizona, which is a really conservative place. And I've had these conversations with people over there, and they'll ask me questions, and I will tell them what I think, and they'll say no. And I'm like, you asked me what I thought. I told you what I thought. I told you that this is all real. I can take you let's go to Greenland. We'll go walking around on the ice sheet, and we can look for this stuff. And if they don't believe it, they don't believe it. I will get into those discussions with certain people if I think they're actually asking me legitimate questions. But otherwise, if they already know the answer that the Earth is flat, there's nothing I can do. There's just nothing I'm going to do.
That's a valid point. Yeah. If they've already been convinced or they're looking for validation, anything you say is not going to convince them otherwise.
Right. I mean, and if they ask me what I think, I'll tell them, and I'll lay the story out. We had the argument about whether SpaceX has been doing all this launching. I'm like, well, this is what I've seen, and you can see this from my front porch. I can see the spacecraft go overhead because we're right near Vandenberg. I can see the thing separate, and I can see the one come back down to Earth. So you can't tell me that's not what's going on. I saw that. And they get in an argument over whether or not we can actually do that, and the technology exists. And conversely, there's the people that believe there are aliens, in Area 51, and it's the same exact conversation, except it's the other way, which is no, I don't think that. So it's the internet. I always thought when we had access to all information that we'd be smarter, and I don't think that's necessarily true.
Yeah, I'm gonna agree with you. I think it just is divided, opinions more. The internet, with endless information, like you said, knowledge is power. But even with all that knowledge, it seems that we cannot.
Well, here's the problem. The internet comes down. So no matter what you do, you're going to make a certain percentage of people unhappy, right? No matter if I'm going to give everybody in America $10,000, there'll be a certain percentage of people that are unhappy about that. And let's say that's 0.1% of the population. And let's say that 0.1% of those people actually write on the internet and complain about it. So you've got 0.1% unhappy, 0.1% going to say something about it. That's a very small percentage. But if there's 400 million people in America, that's 4,000 people on the internet screaming. And you're going to see the 4,000 people on the internet screaming and saying, you're wrong, you're wrong, you're wrong. And eventually you're going to think that's everybody. And that's not true. It's just, it's a very small percentage of a very small percentage. And you just have to continue to do that and not read the comments.
True. Words to live by. Don't read the comments. It becomes a little bit of an echo chamber. So it's best.
Yeah. And in my day growing up, people would, you'd have people on the street corners saying stuff. Now they find each other. So it looks like there's more of them. I don't believe there's more of the fringe element. It's just they now know where to look. It doesn't make me happy, but.
All right. Well, I digress. I apologize. I got us off on a tangent there. But I was curious, after your long tenure at JPL, you transitioned and you moved to Northrop Grumman. What motivated the change?
Just something different. Like I said, I came out here to be here for 1 year back in 1997. I had moved every 4 or 5 years. And if you look at my career at JPL, I kind of switched careers every 4 or 5 years. I did something different.
Mm-hmm.
When I first came out of JPL, I was doing aeronomy, which is like the study of planetary atmospheres. Did that for a while and then moved on to something else and then moved on to something else. And I just always looking for something different because, short attention span theater is kind of what I like. And so went down to Northrop Grumman, worked there for a year or so. It's really hard. It's a really great place. I enjoyed all the people there. I enjoyed the work, but that hour-and-a-half commute one way every day is just something that some people are wired for, and I'm not one of them. And it really took away from my ability to be productive. But yeah, the basic research down there, they do some really cool stuff. It's all DoD related, and that whole group down there is spectacular. Luke Sweatlock is the leader of them in there. He's just great. It was a pleasure to work down there.
Mm-hmm.
Learned a lot.
So what does, things look like for you now? What projects are you working on?
I do a lot of consulting now. I've been helping people. I've been reviewing proposals for people who are submitting to different NASA calls. They'll call me up and they say, "Can you look at my proposal?" And then I will give them feedback, and they can decide whether they're going to use it or not. I've been helping other people write papers. I am a co-I on a proposal that was funded out of Langley, Neural and company. Out there, it's the Sucr proposal, SUCR, and it's the next generation Raman. And so what we're trying to do with that is trying to develop an instrument for the moon that can detect non-lunar material and, interesting lunar material in the sub parts per million range. And that's been really cool because it's been fun to work with new people and tell them what my observations are and talk to them, and they'll ask me a question. Well, why can't we do this? I'm like, well, you could, but you can do this as well. And it's just fun to do that. And I really enjoy that group at Langley. And beyond that, I do a lot of volunteer work. I've been cleaning trails up on the mountain. I talk tomorrow to a bunch of high school and college students to do mock interviews for finding jobs, and doing a lot of nonprofit work for Ability First, which is a local charity that helps disabled and special needs children integrate into society. That's been really fun too. So doing just a lot of fun things and walking my dog a lot. My dog likes to walk.
Well, I love the philanthropic work. The organization that you're working with, like you said, the special needs kids and getting them into different areas of society. What was that organization?
Ability First. It's a local. It's a Southern California nonprofit. Yeah, they do some. We do some great things. It's a great charity. Okay.
All right. Well, I'm going to have to look into that. It's close to my heart. So if there's, hey, something that I could get involved with, that might be of interest for myself. Let's see. We've got a question here. Let's see. DMS asked, is it possible to sample the water that's on Enceladus to detect life? And I think that's a condensed version of the question.
Yeah, you can. So there's a geyser. There is material being thrown off from the tiger stripes in the southern hemisphere. I think it's like 400 kilograms a second of material that's flowing off into space, and it's making part of the E-ring. And we've seen this on Cassini. We see that it's still going on today, and all of that material will be coming up from the ocean. So what you could conceivably do, and there's at least 3 concepts of this that have been flown around out there. We looked at one about 10 years ago. We called it Life, and there's a paper on it. There's other people that are developing now for New Frontiers concept. And the theory is you can fly through the plume and pick up the material and then determine whether anything's alive in that fly through. It's got a lot of technical challenges. You have to be able to, while you're going 8 kilometers a second, fly at like 40 kilometers above the surface and fly within like 50 meters of where the vent is. So it's a really challenging mission. And then you've got to be able to detect almost single cells of life and it's a really cool thing if you can do it, and that would be the easiest way to find out whether there's extant life on Enceladus without having to land. The problem with all of those missions out in the outer solar system is you're going so fast to get there in a reasonable time. It takes 7-10 years to get to Saturn, I think 5 to 7 to get to Jupiter. You've got to slow down when you get there in order to land, and that becomes the problem. And so if you can just fly through it, maybe fly through it several times, that's a cool mission. And there's a lot of people looking at how to do that.
That's very cool. That's not what I'm as familiar with.
And you're flying through fast enough that you should be able to break up. One of the things there, if you fly through too slow, you get a single cell that comes in. How do you detect it? If you fly through fast enough, you might be able to break up that cell, and then the stuff gets vaporized, and you can mass spec it. And that would be really cool. And that's a really cool concept to that has a chance of working.
Very cool. Well, speaking of some of the cool, exciting missions, things that are coming up, what are some of the advancements? I mean, you're obviously still involved in the industry. You're working with different organizations. What are some advancements in technology, specifically as it relates to space exploration, that you see as a significant milestone in planetary science and search for life in the future?
So with all of this, I've been on several juries, and during the jury selection process, they all talk about like the CSI-ification of juries, which is the CSI people come in, they scoop the room, and then they detect all the DNA in the room. It's easy. They go back in like 2 days, they come out with the answer. And in reality, all of that takes a lot of time. The analysis, the sample processing, the sample handling of everything, it's a lot of work that goes into it. So the one thing you need to keep in mind, and this is one of the reasons why Perseverance is designed the way it is. If I see a rock 20 kilometers or 20 meters away that looks like a stromatolite, something that has life on the Earth that we would want to go look at, you got to be able to drive over to it. You got to be able to take a drill and drill into it. And then you've got to take that material and then you've got to process it so how the analytical instruments want it. And then the analytical instruments have to be able to be non-specific enough to be able to detect things. So everything's got to get smaller. Everything has to get less power. And all of that stuff that has to happen between seeing the rock and getting the samples back to Earth has to be automated. And that's money. Every time you say, and this and that, think $10 million or $20 million.
Again, cha-ching again.
Cha-ching. And so when you're doing all of that, and you can do it on the Earth, the problem with doing it in situ is that, like I said, you have to make up your mind on what you think you're going to see before you actually see it. And you've got to do that 10 years in advance. So from what we found from Curiosity and Perseverance, there's some really good instruments that could fly on a life detection mission to Mars, because they already have we're starting to understand the chemistry. One of the things that Viking did not do right was we didn't understand the basic chemistry of the surface before we sent an instrument there to go look for life. And they're still arguing to this day on whether or not Viking found life. But now that we understand the chemistry a lot better, we understand that it's an oxidizing environment. We kind of understand what that oxidant is. We understand what kind of minerals are on the surface. You can now start developing technologies that have a much better chance of actually doing what you want to do. And so a lot of it is just taking what you do on the Earth, some of these instruments are the size of rooms, and shrinking them down to suitcase size or shoebox size, and then automating the entire process from there, and hoping you're right of what you've guessed, because you have to guess at least sometimes. It's an educated guess, but of what the material is most likely is that you're going to go look at.
Okay, a couple questions come to mind, but first, okay, you said the instruments are the size of a room, and you need to shrink those down. Is the goal for the future to get those just as small as possible, to get that room to something much smaller, to, very tiny? Like, how does that continue to evolve over time?
It depends on what NASA, the direction NASA headquarters wants to go. They can either fund the miniaturization and automation of instruments, or they can fund sample return and then bring them back. And those instruments can be as big as you want them to be. They can be bigger than houses. You can, so you have a choice. So it's really if we think those samples on Perseverance are the greatest things ever, then my argument would be then bring them back and develop the instrumentation, in there, or we get to continue to fund instrument development through projects like Picasso and Dolly and Matisse. Somebody at headquarters has a sense of humor, and those are all instrument development proposals. And so it's really how you envision the program going, but you can't. Part of the problem is you can't stop and start. So we did a lot of work back in the early 2000s using microwaves to extract organics from solid samples. All of that knowledge is lost now. So if we wanted to go back to that, their learning curve would be pretty sharp. So you either continue to do it or you continue to do sample return, and that's really what your choices are. And it's largely driven by funding. Instrument development takes a lot of time and a lot of energy and a lot of money to do correctly, because everybody wants to then build an instrument and take it out in the field. So we took the predecessors to SHERLOC out in the Mojave. We took them out multiple times to show that we can actually saw what they showed. And a different group took SHERLOC to Svalbard and Antarctica, and you take it out and actually try to detect life on Earth. There's groups doing that right now. There's a group out of Ames that is their whole Camelot Excalibur thing. And we love our acronyms, and they're building an instrument. They're trying to shrink it, and they're going to take it out in the field and show that it can do what it can do. Because if you can't identify life on the Earth, you're not going to detect life on Mars or anywhere else.
Can't do it here. You're not going to do it there.
Yeah, this is pretty easy here.
I have a question from one of my fellow students. What is the detriment of not collecting samples before sending humans to Mars? I think you touched on this earlier, but let's expand on that.
So what Apollo, the number one thing that comes to mind, and they do studies on what you have to know to send humans to Mars. There's studies every 2 or 3 years. You can go online and look for them. MAPAG has it. MAPAG documentation has it. This is what we need to know to send humans to Mars. And the different priorities depending on who's in the room. So different people think different things are important. What everybody agrees on when the Apollo mission took place, and there's a great picture of Gene Cernan with lunar dust all over his face. When they went out and they came back in, there was no way to get rid of the dust except, and they breathed it all in. On Mars, the dust is just as bad and just as prevalent, and it's completely different because it's in a different environment and it's been around different things for a longer period of time and a different formation mechanism. Anybody who lands on Mars is going to breathe that stuff in. And if that stuff, it consists of 10 micron sharp little edged particles of perchlorate, or is something close to asbestos, the people are not going to be happy with that because they're not going to live much longer because they're going to breathe a lot of it in. You need to know what's in it, and you need to characterize it. You need to see what dust particles are, how big they are, both the atmospheric dust and the stuff and the regolith on the surface, so you can plan things around it. You can actually make hardware and other things that will deal with that. One of the things we did on SHERLOC, and our calibration target on SHERLOC has 5 pieces of humans to Mars material for visors, for gloves, and we're exposing that to the Martian environment to see how it breaks down over time, because no one's done that before because it's a different environment. You need to know all of that stuff so you can say to the people you're sending, don't worry about it. It's either safe to breathe, or this is how we're going to make sure you don't breathe it in. And if you don't do that, it's no bueno. no bueno is the best way to say it.
Yeah. Well, thank you for elaborating on that. That makes a lot of sense. My mind goes to, somebody out there is going to try to invent something to remove that dust. They're going to try to create some special filter or some sort of, vacuum to collect all that dust. So in the option that they can't bring those samples back first, if the mission is just get humans there, how do we evolve so that we're going to send them first anyways? How can we protect them from that dust?
So I've been to the Mojave, I've been to other deserts, I've been to Greenland, I've been to Oregon. Different material in different places on the Earth is different, and so we need to characterize what's on Mars, and then we can start developing that stuff. And I think that's what the lunar mission showed as well. So bring it back, characterize it, see if it's a problem, see how big of a problem it is, and then move on from there. But you have to do that if you're sending people.
There's a follow-up question. Could suits ports solve the dust issue to a large degree?
Maybe, and that's the problem. Is the answer is maybe for all of that. How you can invent something from a spacesuit humans to Mars thing that could maybe work 98% of the time or 99% of the time, but are you willing to bet on that?
Yes, it's not a catch-all. It's to solve that completely.
Yeah, it really depends on sample return and bringing back both the atmospheric and the regolith samples. I don't know how you do humans to Mars without it.
Well, let's see. When's assuming those samples do get returned, whether it's NASA, it's a commercial company that brings those back. How do those samples get disseminated for investigation? It goes to NASA and like whoever raises their hand gets a piece of it. Like, how does that process?
That's a great question. I think what they would end up doing is they would build a containment facility on the Earth. The samples would not necessarily leave the containment facility. Maybe, I don't know. This is the way I would kind of do it. And then I would have people develop hardware that went in and never came out. And then you would basically do with the robotic arms, move and modify the samples and put stuff in that is pretty clear. I don't know what the cost of that facility is. You're talking billions on that as well. And then what people would do is they would propose to that. So it's the same way they do the instruments, which is, hey, right now there's an Apollo sample call. We want a piece of Apollo to do this with, to explore this. This is what we want to do. This is how we're going to do it. This is what we're going to do with the rocks. And then it gets reviewed by peers, and then they select people that get it. So that's what you would have to do.
Okay. Yeah, there's a process for that, and yeah, you have to put in your proposal for the research that you potentially want to conduct.
Yeah, how much it's going to cost. Does the sample get destroyed in the process? So sometimes they're more likely to give to people that just have visual odometer or visual instruments and things like that.
Okay. Well, I know we're coming up on our hour here. Looking forward to the future, what are you excited about? What are you optimistic about in terms of space exploration, getting humans to Mars?
I think there's the James Webb has launched. Nancy Grace Roman is launching next week. This is all astrophysics, or not next week, but soon. I can't wait for those things to come out. I've been watching all the James Webb publications come back. Those are all great. There's Dragonfly in a couple of years will be awesome to see. I can't wait to see the results from that. And then just how the community changes around the new financial. We've only got money to do X number of things. What are we going to choose to do? Because if you do sample return, you might not be able to do Uranus. And that would be a shame because Uranus is really cool. But once again, you've got a fixed number of dollars to spend. So it's just fun to watch all this stuff come down.
Absolutely. Well, there's a lot to be excited about, and although it's a changing of the guard, we're seeing like Jared Isaacman, for example, getting potentially nominated, and he's a big advocate for Mars as well, and pushing the boundaries of where human exploration has gone so far.
Yeah.
So there's something to be excited about.
Yeah, in my lifetime, when we went to the moon a few times early in my lifetime, barely remember it, but we need to get out of low Earth orbit. We need to go somewhere. Just let's go. Let's go explore. The last Calvin and Hobbes has the let's go exploring one, where Hobbes has grabbed Calvin by the hand and they're going exploring, and that's exactly what we need to do. Let's go do stuff. Let's go do it.
I love it. Wholeheartedly agree. Absolutely.
Yeah.
Well, Dr. Beegle, thank you so much for being here today. I really appreciate your time and answering all of our questions. We got through most of them, and you were a trooper getting through all of those for us.
Thank you very much. I really appreciate it. It's been great being online with y'all.
Yeah, such a pleasure. Well, special thank you to our leadership, Executive Director James Burke, our PR Director Michael Stoltz, our behind the scenes whiz, Leah. Thank you so much for your help today. And thank you everybody that has tuned in to today's episode. And I'm going to close out today like we always do. You've heard me say it. I'm going to say it again. The best is yet to come. Thank you, everybody.
Absolutely.